In this video, we're going to expand upon our understanding of what a chemical reaction is, and more importantly, how to identify when a chemical reaction has taken place. In the previous video, we defined a chemical reaction as being any time the chemical structure of at least one of the reactants involved in a reaction is altered in some way. Now, this is particularly easy to observe when we look at the chemical structure of covalent compounds, because we're actually able to see the bonds and any changes in the bonds that hold the atoms together that occur during the reaction. And we can actually take a look at a fairly common type of reaction involving CH3COOH, which is this compound down here. This is actually the chemical formula for vinegar. Now, vinegar behaves as an acid when it is put into water, meaning that vinegar reacts with water in order to produce a chemical that gives vinegar its sour flavor. And this is true of all acids. This is why lemon juice or orange juice also have a distinctly sour flavor, because of the acid that's present in both of those juices. So what happens at the atomic level is when water gets close to vinegar, water can actually use its lone pair in order to make a bond with this hydrogen here on vinegar. The problem is that hydrogen can only make one bond, meaning that CH3COOH is actually going to have a bond broken in this chemical reaction, where this bond breaks and the electrons in that bond will actually become a lone pair here. And we can see on the product side that this bond was definitely broken because it is no longer there. Now, conversely, if we take a look at water, we can see that the oxygen in water has two hydrogens bonded to it in the reactant side, but we can see that there is a new bond that is made between the hydrogen that used to be on vinegar, and this bond now connects it to the oxygen in water. So we can expand our definition of any change to the chemical structure to mean any time there is a breaking of a bond, or anytime a new bond is created or formed in the process of the chemical reaction. And the reaction between vinegar and water is an easy example of this happening. The problem is, when you look at a bottle of vinegar, you're not actually able to see this chemical structure, nor are you able to see the actual reaction at the atomic level involving the breaking and making of bonds. So the problem is, if we can't see new bonds being broken or bonds being made, how can we tell that there's actually a chemical reaction that has happened? Well, the answer I've actually already given you, because vinegar happens to be an example of a chemical that we can actually taste. And if you taste vinegar before and after the reaction, that difference in taste tells us that a new chemical was produced in this reaction. Well, obviously, since it's probably not a good idea to taste every chemical that we react, we need a bunch of other easy to make observations that can identify whether a chemical reaction has happened. And probably the most easy one of these to recognize is a color change, where the reactants and products of a chemical reaction simply are different colors. And we can take a look at this sample reaction here. So silver nitrate and sodium chloride, yes, this is simply salt dissolved in water. These are both examples of solutions, meaning that both of these are ionic solids that are dissolved in water, but both of these appear colorless. But when the two are reacted together, the metals in the reaction actually switch places, causing us to get sodium nitrate that also happens to dissolve in water, so we're not going to see anything here. But when silver chloride is produced, this produces a very distinctive cloudy white substance that is clearly different than the colorless solutions that were mixed together. And the fact that this color was not there before clearly indicates that the chemical structures of our two reactants have been altered in some way. Now, the observant among you will also recognize that I labeled the state of matter of silver chloride as being solid, while both of the reactants were dissolved in water. That's what the AQ means. AQ is short for aqueous, meaning dissolved in water. This is actually a second example of a recognizable change, that being the formation of something that we call a precipitate. So a precipitate is a substance that is solid that forms when two dissolved substances, meaning two solutions, in this case silver nitrate and sodium chloride, are mixed together. And even though each of those compounds dissolve in water, the product that is formed does not. And because it does not, this is clearly an example of a new substance that has been produced. And solution chemistry is often quite exciting because a lot of the precipitates that we can see are very visually striking, both in terms of how obviously some don't dissolve in water and in terms of the variety of colors that we can end up seemingly out of nowhere. But what about if we're dealing with substances that aren't actually solid? So here, if we take a look at what happens when we drop zinc metal into highly concentrated hydrochloric acid, we can see that this reaction is producing bubbles on the surface of the zinc as it reacts. So in this reaction, zinc and hydrogen actually switch places. One of the compounds is fairly unspectacular. Zinc chloride actually dissolves in the acid here, but the bubbles that we're observing are actually hydrogen gas. And obviously, zinc and hydrochloric acid, neither of these are gases, so these bubbles indicate that a gas is produced where one did not exist before. And this gas doesn't necessarily need to be hydrogen, but the fact that bubbles are appearing seemingly out of nowhere indicates that this reaction produces a gas that wasn't there before. The second to last observation that we can make is often the most exciting to witness and also potentially the most dangerous, and we can summarize this as being changes in energy, although a lot of people like to simply refer to them as changes in temperature, but that's kind of a little bit too specific for this. So if we take a look at the two sample reactions, one of which is the burning of magnesium metal in the presence of oxygen gas, and you can actually buy magnesium that comes in thin wire strips, and if you burn this in a hot enough fire, it will produce a distinctive white powder, magnesium oxide, and again, that's an example of a color change because magnesium is kind of a silvery gray color, and oxygen is colorless because it's a gas, so the color change is one evidence that a chemical reaction has occurred, but also this brilliant white light is probably the most striking example that there is a major change in energy that is being observed. In fact, it's not just light, you'll also feel an intense heat because magnesium burns at over 3,000 degrees Celsius, which is comparable to the heat of some stars. So, needless to say, very dangerous. However, humans have harnessed this particular reaction to use in fireworks because of the brilliant white light that is produced when magnesium is burned. For a more simple example of a reaction, we can take a look at what happens to hydrogen gas when it is burned in the presence of oxygen. This is actually how we get water that is produced, but more importantly, we would actually see that fire is produced from this, and you'll also hear a sound. This will often be accompanied by a small exploding sound or a popping sound, kind of like a cork being popped or a very, very low caliber gunshot. And again, both of these indicate that a large amount of energy is being released by the chemical reaction. So even though we can't perceive changes in energy directly, we will recognize, or we can recognize, that an energy change is observed whenever we see light, whenever we feel heat, or whenever we hear the sound of an explosion that comes from this energy change. And finally, kind of peripherally related to vinegar, even though we can't use our sense of taste most of the time when working in chemistry, we can use our sense of smell. And this is particularly common when dealing with organic compounds, because many organic compounds have very, very distinctive scents about them. So in this example here, C2H4 is a relatively unexciting example of what we call a hydrocarbon, which is a simple organic compound that doesn't really have any scent at all. And of course, water is famous for its lack of scent whatsoever. However, when we react these together, we actually can produce alcohol, or more specifically ethanol, the alcohol that is used in beer, wine, etc. And many people report alcohol as having a very distinctive smell, especially when in high concentrations. And because neither of the reactant substances had any particular smell, but alcohol does, that is a good indicator that we have produced a substance that did not exist before. This concludes this video, and hopefully you can use the observations that we've talked about to distinguish whether a chemical reaction has taken place. So before you move on to the second topic in this series, you can try the practice problems below to see whether you can distinguish whether a chemical reaction has or has not occurred.